Welcome learners to the GATE coaching on digital electronics. This is Satya, Assistant Professor, EEE Department, S.A.E. Engineering College. In digital electronics, particularly we are going to see analog to digital and digital to analog converters. And outline. First, we need to see what are all the need conversion of analog into digital and digital into analog. Then we are going to see the block diagram of converting analog to digital and its types with some problems. Similarly, DAC and its types with some problems. First, what is the need for analog to digital and digital to analog conversions? All the original signals by nature are analog. Whatever may be the signal, voice, message, text, or any change in parameter, everything are changing with respect to time, analog. But the available systems are nowadays completely digital. So that definitely there is a need to convert the analog original signals into digital. And similarly, after processing, there is a need to convert it back into digital for presentation. So first, the block diagram of analog to digital converter. There are 3 steps in converting an analog signal into digital: sampling, quantizing, and encoding. This can be explained easily with the help of this diagram. So the first signal is nothing but an analog signal, which is continuous in time and continuous in amplitude. That is, the signal is defined for every instant of time. So the first process in converting an analog signal into digital is sampling. So instead of taking every signal at every instant, we are going to take only the samples at discrete points. So thereby we are converting the signal as discrete in time, but still it is continuous in amplitude. So next step is quantization. Quantization is approximating the amplitude to the nearest discrete voltage level. So in this case, some voltage, discrete voltage levels are fixed, and all the samples amplitude which are close to these discrete voltage levels are approximated. So thereby we are converting the signal discrete in amplitude also. So now the signal which is discrete in time and discrete in amplitude is the output of quantization. Next process is encoding, where we are going to assign binary digits to the discrete voltage levels. Encoding. So this is how the analog signal is converted into digital sequence of data, digital signal. So coming to the types of analog to digital converter, dual slope is the method which is going to produce more accurate result, but this is going to be a slow process of converting an analog into digital. And the next method of flash A to D converter is going to be very fast, but the disadvantages is it requires 2 power n minus 1 comparators for n bit conversion. And the next is successive approximation method, which is going to be very fast compared to that of above 2 methods. So coming to the first problem, 8-bit analog to digital converter, where the analog voltage is going to be in the range of 0 to 5 volts is given. And the question is, what is the digital output corresponding to the input analog voltage of 1.9922 volts? So as I said, the analog signal is converted into samples, then quantized, and after that it is assigned to some binary digits, which is in hexadecimal here. So the question is, what is the value, hexadecimal digital output value corresponding to Vin of 1.9922 volts. So the equation which is going to give you digital output corresponding to analog input is this: digital output is equal to 2 power n, where n represents the number of bits. Here the number of bit n is equal to 8. So 2 power 8 into analog input voltage, for which we are going to determine digital output is 1.9922 volts. Next, divided by the reference voltage, that is the maximum voltage range, which is 5 volts in this case. So using this formula, we are getting a value of 102, digital output of 102 in decimal, but the output is given in hexadecimal, so definitely we have to convert it into hexadecimal using this method. That is 16, 6 are 96, balance 6. So it is going to give you 6 in hexadecimal. So 1 or 2 is converted into hexadecimal, which is 66. So the option C is the right answer here. Next problem is coming to the flash type analog to digital converter, where a 2-bit flash analog to digital converter is used. As I told, this method requires 2 power n minus 1 comparators. Here, number of output bit is equal to 2. So 2 power 2 minus 1, that is 4 minus 1, 3 comparators are used in this case. So here the total voltage of 3 volts is divided along the voltage divider resistance network, and thereby we are going to get different voltage values at the second terminal of the comparators, whereas the first terminal is going to be connected with the input voltage V, which is varying from 0 to 3 volts. So the question here is to find out the expression for B0 in terms of X0, X1 and X2. So this digital circuit is nothing but an encoder which converts the binary digits X0, X1, X2 into B0 and B1. So what are the voltage, different voltage values at the second terminal of the comparator is represented here. In case of voltage divider rule, we can determine what is the drop at each resistor in this circuit. So what is the voltage across first resistance 100 volts? It is, if it is represented by V1, then V1 is equal to the total voltage V into the resistance across which we are going to measure the voltage divided by the total resistance. So the total voltage here is 3 volts and the resistance across which we are going to measure the drop is 100 and the total resistance is 600. So we are getting 0.5. So 0.5 is the voltage drop in 100 ohms. Similarly, we can measure the voltage drop in 200 ohms resistor, which will give you 1 volts. So a drop of 5 volts is going to give you 2.5 volts here, and a drop of 1 plus 0.5, 1.5 from the total voltage of 3 volts will give you 1.5 at the second comparator. And another 1 volts drop will be there in the third resistance. So totally 1 plus 1 plus 0.5 is going to take nearly 2.5 from the total voltage of 3 volts. So we are getting only 0.5 at the third comparator. And the comparator is going to produce a logical 1 if the supply at the positive terminal is more compared to the supply at the negative terminal. So the voltage at positive terminal is if greater than the negative terminal, the comparator is going to produce a logic 1. Otherwise, it is going to give you 0. Consider the input voltage, which is going to be in the range of 0 to 3 volts. Consider the first case where the input voltage is 0 volts. So 0 volts at the 3 positive terminals of the comparators is going to give you only 0, 0, 0. That is the first sequence in the encoder table. So next, if the input voltage is 1 volt, then we are going to have a 1 volt here. So here this comparator is comparing. So the 1 volt is greater than 0.5. So this is going to produce a logic 1. But coming to these two cases, the voltage is 1, which is less than 1.5 and less than 2.5. So it is, these two are going to give you 0. So that we are getting the second logic 0, 0, 1. And if the input voltage is 2 volts, then these two comparators are going to produce logic 1, whereas the first is going to produce logic 0. And the last case is when the input voltage is 3 volts. When the input voltage is 3 volts, definitely all the 3 comparators positive terminal voltage is high compared to the negative terminal voltages of 0.5, 1.5 and 2.5, so that we are getting 1, 1, 1. So the last logic. And the output of B0 and B1 is going to be 0, 0, 0, 1, 1, 0, 1. So the question is to determine the expression for B0 in terms of X0, X1 and X2. So the B0 equal to 1 for the logical combination of x2 bar, x1 bar and x0 plus another one we are getting for this combination of x2, x1, x0. So by summing these two, we can take the x0 in common, so that we are getting x2 bar, x1 bar plus x2, x1, which is equal to XOR operation of x1, x2 and x1 bar. So the output is option A, x0 into x2 XOR x1 bar. Next problem is in case of successive approximation method. An 8-bit unipolar successive approximation register is used, and it is used to convert the 3.5 volts analog voltage to digital equivalent. And the question here is, what is the output bit pattern at the end of third clock pulse? So this is the circuit for successive approximation register method. So on receiving the start of conversion signal, the successive approximation register is going to initialize all the bits to be 0, 0. So here the number of bit n equal to 8. And we can also determine the resolution with the help of reference voltage. Reference voltage VR is given as 5 volts. The reference voltage is given as 5 volts. So, and number of bits 8. So with the help of this, we can determine the resolution, which is equal to reference voltage divided by 2 power n minus 1. Here 2 power 8 minus 1, which is going to give you nearly 20 millivolts. So with this resolution, on receiving the SOC signal, the bit pattern is all zeros. So when the first clock pulse is applied, the register is going to make the most significant bit as 1. So with this pattern, the output is given to the digital to analog converter. The digital to analog converter is going to convert the digital bits into proportional analog voltage, and that is compared with the input voltage. So what is the digital voltage corresponding to this particular analog voltage corresponding to this particular digital pattern? It is equal to 20 millivolts, the resolution, multiplied by the binary equivalent, decimal value equivalent to the binary pattern. That is, if this position is 2 power 0, 1, 2, 3, 4, 5, 6, this represents 2 power 7. So 2 power 7 multiplied by 20 millivolts is going to give you 2.5 volts. Now the 2.5 volts is compared with that of the input voltage of 3.5 volts. So the comparator is going to keep the bit pattern as such for the next cycle. So when the second clock pulse is applied, then the successive approximate register is going to set the next most significant bit as 1. So we are getting this particular pattern, and the digital voltage corresponds to this pattern is nearly 3.75, and that is taken and compared with that of input voltage 3.25. 3.5. So now the comparator here to input voltage is 3.5, and the output voltage that is coming out of DAC is 3.75. Now the voltage at this terminal is less than that of the voltage at the voltage VD. So in this case, the bit pattern is going to change. That is, the second most significant bit which is set is now reset. Next, during third clock pulse, the successive approximation register is going to make the third bit as 1. So this is the bit pattern after third clock pulse from this successive approximation method. So the option A is the right answer, 1010 0000. So next block diagram of digital to analog converter. The input which is coming here is the digital input, that is binary sequence of ones and zeros bit stream, and that is given to the voltage switching device, which is going to switch the voltage according to the binary pattern that is coming inside. That is, if the binary bit is 0, then it is going to switch off the voltage, and if the binary bit is 1, then it is going to make the voltage according to the reference voltage. The pattern is going to switch between 1 and 0 according to the bit pattern, and that is added in the summing circuit and rise to the required amplitude and represented as the corresponding analog voltage to the given bit pattern. And these are the types of digital to analog converter: binary weighted resistor, R2R ladder, and delta sigma tags. So let us consider a simple problem in DAC. Consider a 4-bit digital to analog converter. The analog value corresponding to digital signal values of 000 and 0001 are 0 volts and 0.0625 volts. That is, the voltage corresponding to this pattern is 0 and the voltage corresponding to the next pattern is 0.0625. From this, it is very clear that 1-bit position voltage is, which we are calling as step size, is 0.0625 volts. With the help of this step size, we can measure the analog voltage corresponding to any digital pattern. So the digital pattern given here is W1 W1. So W1 W1 is going to give you a decimal value of 2 power 0 plus 2 power 1 plus 2 power 2 plus 2 power 3, which is 15 in this case. So the decimal equivalent of the given bit pattern 15 is multiplied by the step size to get the corresponding analog output voltage of 0.9375 volts. And next problem is weighted resistor, 4-bit weighted resistor DAC with 4-bit B3, B2, B1 and B0 from represented from MSB to LSB as shown in this diagram. So the question here is, when the input voltage is B3, B2, B1 is equal to 1110 and W101, what is the change in voltage, analog voltage, that is occurring in this case? So coming to this diagram, this is a weighted resistor DAC. Here, this is nothing but operational amplifier, and the output voltage V0 is equal to, V is equal to I into, what is the total current coming here, I into minus R. So the V0 is equal to minus R into the current in all the parallel paths. So what is the current in the first path? It is I equal to V by R. So that is V reference divided by R is the first current. V reference divided by R. Why it is multiplied by the bit pattern B3? Because the bit pattern is going to decide whether the switch is going to close and thereby contribute to the total current, or if the bit pattern is 0, then it is going to open and it does not produce any current to that path. So according to the bit, we are going to multiply the B3, B2, B1, B0 with that of the current expression. So we are having a I1 as V reference by R, I2 is V reference by 2R, I3 V reference by 4R, and I4 is V reference by 8R. So this is the expression which we are having for output voltage V0, and by taking V reference and R outside, we can cancel these two resistors, and the output voltage is minus V reference into the bit pattern divided by the resistor value. So for the bit pattern of 1110, we are getting the output voltage V0 as minus 2 into, and B3 is 1, so 1, B0 is 1, so 1 by 2, pattern B1 is 1, 1 by 4, plus as the bit B0 is 0, this particular term is going to become 0. So on solving this equation, we are getting a minus 3.5 volts output voltage, and for the next binary sequence of W101, we are going to proceed in the same case, and we are getting a voltage of minus 3.25. The question is, what is the change in voltage in the 3 consecutive cases? So the change in voltage is 3.5 minus 3.25, which is equal to 2.25 volts and 250 milliamps. Thank you for listening. Meet your video session. Happy learning.